In this lecture, we look at some additional examples in probability. This will be the concluding lecture in this course on Introduction to Probability and Statistics. We look at some new examples and we try to explain some interesting ideas from problems that are well known, and we are going to look at 5 to 6 different examples in this lecture. Some of these have already been covered in earlier lectures, and I will also try to give some additional explanation or an alternative way of solving the problem. So, we begin with this problem. 2 balls are chosen randomly from a bag containing 8 white, 3 black and 2 red balls. You win ₹10 if you choose a black ball and lose ₹2 if you choose a white ball. Let x be the return. What values can x take? What are the probabilities? What is the expected value? And if you can play this game 3 times by paying ₹10, is it profitable? What is the probability of winning? Since 2 balls are chosen, there are 8 plus 3, 11 plus 2, 13 balls. So, the 2 balls could be chosen as white and white, black and black, red and red. It could be white black, black white. It could be white red, red white. It could be black red and red black. Now, the corresponding gains are given. So, -4 because you lose ₹2 if you choose a white ball. So, if we do a WW, then it is -4. So, the gains are written here -4, 20, 0, 8, 10 and -2. Probabilities are also given alongside. So, probability of WB and BW both are added and they are given here. You could also check that the probabilities add up to 1. So, the expected return would be the value of the gain multiplied by the probability, that is -4 into 0.359 plus 20 into 0.038 and so on, which is 3.684 with the variance of 47.91. Now, the cost is to play 3 times. We can play by paying ₹10. So, the cost is 3.33, the expected return is 3.684, therefore, it is profitable, and the probability of gain is the sum of the probabilities where the return is positive, and therefore, we get 0.551. So, more than half the time there is a chance of making some money in these trials. We come to the next question. 5 distinct numbers are randomly given to 5 persons. So, persons 1 and 2 compare their numbers and the winner is the one having a bigger number. The winner then compares it with person 3 and so on. What is the probability that person 1 wins 0 times, 1 time, 2 times, 3 times and 4 times? So, the solution is, let the numbers be 1 to 5 and let n1 be the number the person 1 gets and so on. So, the numbers are 1 to 5, the persons are also called 1 to 5. So, person 1 will win 4 times if person 1 gets the largest number, because irrespective of who person 1 compares and starts comparing with 2 and then wins and then compares with 3 and then wins and so on, that can happen when person 1 gets the largest number, which is 1 by 5. Person 1 will win 0 times if n1 is less than n2, which means the number that person 1 gets is less than the number that person 2 gets. So, this can happen in many ways. Person 1 can get number 1 while person 2 can get anything from 2, 3, 4 and 5. Person 1 may get number 2 and person 2 may get numbers anything between 3 and 5. Person 1 may get number 3 and person 2 may get 4 or 5, and person 1 may get number 4 and person 2 gets number 5. So, the probabilities are person 1 getting number 1 is 1 by 5, which means person 2 will get anything from 2 or 3 or 4 or 5. Person 1 getting number 2 is 1 by 5. Now that is multiplied by person 2 getting numbers 3 or 4 or 5, 3 out of the 4 remaining numbers, so 3 by 4. Now person 1 getting number 3 is 1 by 5 and person 2 getting 4 or 5 out of the remaining 4 numbers is 2 by 4, and person 1 getting number 4 and person 2 getting number 5 is 1 by 5 into 1 by 4. So, we multiply and add to get 10 by 20, which is half. Person 1 wins only once, and these possibilities are person 1 gets number 2 and person 2 gets number 1. Person 1 gets number 3, person 2 gets numbers 1 or 2, person 1 gets numbers 1 or 2 and person 2 gets 4 or 5, person 1 gets number 4, person 2 gets 1, 2, 3, person 1 gets number 5, and so on. So, let me repeat, person 1 wins only once. So, this can happen when person 1 gets the number 2 and person 2 gets the number 1, so that person 1 will win, and next time the person will lose because person 3 would have got a number higher. Second case is person 1 gets the number 3, person 2 gets numbers 1 or 2, so that person 1 would win once and person 3 should get 4 or 5, so that person 1, now having won the first round with person 2, now faces person 3 who has a higher number and loses, and therefore person 1 wins only once. The other case is person 1 will have number 4, person 2 will have numbers 1, 2, 3 and person 3 has number 5. Therefore, again person 1 will win only once and then face person 3 who has 5 and therefore will lose. So, the probabilities are 1 by 20 plus 1 by 15 plus 1 by 20, which are calculated in the usual way to get 1 by 6. The case where person number 1 wins 2 times can happen when person 1 gets number 3, person 2 gets numbers 1 or 2, person 3 also gets numbers 1 or 2, so that when person 1 meets person 4, that would have had a higher number, and therefore person number 1 will win only 2 times. The other case is person number 1 gets number 4 and person number 4 gets number 5, then person number 1 would have won only 2 times. So, there are only 2 cases and the probabilities are 2 by 60 plus 1 by 20, which is 1 by 12. Person 1 wins 3 times, means person 1 gets value 4 and the 5th person gets the number 5, so that finally in the 4th comparison person 1 will lose and therefore would have won only 3 times. There is only one case and therefore the probability is 1 by 20. So, this is a very interesting question which kind of makes us think and look at all the possibilities and then list out the number of ways by which these things can happen, and once we are able to get that, then assigning the probabilities and multiplying them and adding them becomes relatively simpler and we can solve such problems. Now, we look at question number 3, which is a question that we have seen earlier. Probability of power cut in a day is 0.05. What is the probability that there is a power cut in the next 3 days? So, this we have seen this slide earlier. Probability of no power cut in a day is 0.95. So, for 3 days probability of no power cut is 0.95 cubed, which is 0.857, and therefore probability of power cut, at least one power cut in the next 3 days is 1 minus 0.857, which is 0.143. Now we can do the same problem using the binomial distribution, and that is the reason why we are revisiting this again. So assume binomial with p equal to 0.05, which is the probability of a power cut, and q is equal to 0.95. So in this case success is like saying there is a power cut, and failure is there is no power cut. So no power cut will be straight away 0.95 cubed, which we have already seen. So this is NCx p power x q power n minus x. So NC0 p power 0 q to the power n minus 0, which is q to the power 3, which is 0.95 to the power 3, which is 0.857. There is one power cut is NC1 p to the power 1 q to the power 2, which is 3 into 0.05 into 0.95 into 0.95, which is 0.135. Two power cuts is 3C2 p to the power 2 q to the power 1. You see 3C2 is 3, p to the power 2 2 times multiplied, q to the power 1 0.007125, and 3 power cuts is 0.05 cubed is 0.000125. So one power cut in 3 days can be seen as yes, no, 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 yes, no, and no, no, yes, which happens 3 times. So therefore we multiply by 3, which comes here, this 3, which is captured in the NCx, which is in the binomial distribution. So finally the answer that we got here is 1 minus 0.857, which is 0.143. So probability of there is one power cut in the next 3 days is 1 power cut plus 2 power cuts plus 3 power cuts, which is equal to 1 minus probability of 0 power cut. So 1 minus 0.857, which is 0.143. So the same problem we now looked at using the binomial distribution, and the idea of 2 outcomes and the Bernoulli trial leads us to the binomial distribution. Now we look at the next question. Again this question we have seen earlier, we have seen this slide earlier. We will now see another way of working out the same problem. So in a card game, a pack of 52 cards is dealt randomly to 4 players. What is the probability that each player gets exactly one ace? So we have seen this description earlier, therefore I will go slightly faster on this description. So if we take the first person, the ace should come in 1 out of the 13 picks. So take the case where ace is in pick 1 and the remaining 12 do not have an ace. So ace in position 1 and no ace in remaining 12 positions is 4 by 52 into 48 by 51, etc., etc., which is 0.03376. 4 by 52 comes because there are 4 aces in 52 cards, and then one card has been picked up, so remaining 51, and then this one should not be an ace. So there are 48 non-ace cards, and therefore 48 by 51, and it keeps reducing for 13 picks and you get 0.03376. Now this ace can come in any one of the 13 positions, therefore 13 into 0.03376 is 0.4388. Now for player 2 it is 3 by 39 because there are player 1 13 cards have been given, so there are 39 cards remaining and there are 3 aces, so 3 by 39 into 36 by 38 because the second position should not have an ace, and so on. So once again it can come in 13 positions, 0.4623. For player 3 it is 2 by 26 because players 1 and 2 we have already used up 26 out of the 52 cards and remaining 26 cards are available, out of which there are 2 aces. So 2 by 26 into 24 by 25 and so on, and this comes in 0.52. For player 4 it is 1 by 13 because player 4 does not have a choice, all the remaining 13 come. So out of these 13 there should be one ace, so 1 by 13, and this can come in 13 positions, so 1. So we multiplied all of them to get 0.1054. Now let us look at the permutation combination way of doing this. So, number of ways by which 52 cards can be given to 4 people, 13 cards each, is 52C13 into 39C13 into 26C13 into 13C13, which is 52 factorial by 39 factorial into 13 factorial. This is 39 factorial by 26 factorial into 13 factorial. This is 26 factorial by 13 factorial into 13 factorial. The last one is 1 because the remaining 13 cards goes to the 4th person. Now, we see something interesting happening. This 39 factorial is getting cancelled, 26 factorial is getting cancelled and so on, and therefore, we get 52 factorial divided by 13 factorial 4 times. If we leave out the 4 aces, 48 cards can be given to 4 people, 12 cards each, in a similar manner. 48C12 into 36C12 into 24C12 into 12C12, which on simplification will give 48 factorial by 12 factorial into 12 factorial into 12 factorial into 12 factorial. The 4 remaining aces as the 13th card can be given to the 4 people in 4 factorial ways, and therefore, each person getting an ace is 4 factorial multiplied by 48 factorial divided by 4 times 12 factorial divided by 52 factorial, which comes here, and the 13 factorials go to the numerator and we get 0.1054. The simplification is also shown here. So, the same problem can be viewed or approached in 2 different ways. I mean, one can critically look at both these and say that they are actually the same, but they are certainly 2 different ways of working out the same answer for problems of this kind. So, we look at a 5th question. A government school gives a 50% fee waiver for girl children. So, your neighbor has 2 children and has admitted a girl child and got the fee waiver. Given this information, what is the probability that she has 2 girl children? So, this is a very interesting question, and first let us solve this and then try to understand a couple of more things about it. So, ordinarily 2 children can be in 4 ways: boy boy, boy girl, girl boy and girl girl, assuming that the child is either a boy or a girl. Given that she got a waiver, the favorable outcomes are boy girl, girl boy and girl girl. We have not spoken about first child and second child, and therefore, we still have boy girl, girl boy and girl girl. Now, probability that she has 2 girl children is probability that of girl girl divided by girl girl plus boy boy, which is 1 by 3. The other way to do is girl girl comes as 1 by 4, girl girl, girl boy, boy girl is 3 by 4. So, 1 by 4 divided by 3 by 4 is 1 by 3. We can also use the Bayes theorem. So, P of or the conditional probability theorem. So, P of A given B equal to P of A and B by P of B. So, probability of 2 girls given a waiver is probability of 2 girls and waiver divided by probability of waiver. So, 1 by 4 divided by 3 by 4, which is 1 by 3. So, we find many problems like this, but then we approach these kind of problems this way. At times the boy girl problems also have different solutions where the order and other things are involved. So, being an introductory course, we would restrict ourselves to this explanation and then follow this idea of solving this problem, even though other interpretations and other solutions exist for what are typically called the classes of boy girl problems in probability. We look at one more question. In a multiple choice test, a student either knows the correct answer or guesses the answer. Let P be the probability that the student knows the answer. Assuming that the probability of guessing is 0.25 because there are 4 choices, what is the conditional probability that the student gets the answer correct by not guessing? So, this has been discussed in Ross and I have given the reference for that. So, let C be the event that the student gives the correct answer and K the event that the student knows the answer. So, probability that the student knows the answer given that the student has actually given the correct answer is the probability that probability of knowing the answer into giving the correct answer divided by probability of giving the correct answer, which is P of C given k into P of k by P of C given k into P of k plus P of C given k transpose plus into P of k transpose. So, probability P of C given k into P of k is P divided by P plus 1 minus P into 0.25. 0.25 is the probability of guessing and not knowing. So, 1 minus P is 0.25 is the probability of guessing, 1 minus P is the probability of not knowing. So, probability of not knowing, guessing and getting the correct answer is 1 minus P into 0.25. Probability of knowing the answer, writing it and getting it is P, therefore, P by P plus 1 minus P into 0.25. So, the numerator is about knowing the correct answer, writing it and getting it with the probability of P. So, you could get the right answer either by knowing the right answer and giving it, or by not knowing the right answer and guessing it. So, knowing the right answer and giving it is P into 1, knowing the right answer and guessing it is P into 1, not knowing the right answer is 1 minus P, and guessing it and getting it right is multiplied by a 0.25, therefore, P by P plus 1 minus P into 0.25. If P equal to 0.6, then the probability is 6 by 7, so 0.857. So, the number of questions that the student knew the answer and correctly answered is about 85% if the student knows the probability of the answer, correct answer is 0.6. If we want the student 90% of the times getting it right knowing the answer, then we back calculate and find out P is equal to 0.692, which is roughly 0.7. So, if the student knows the correct answer with a probability of 0.7 and does the remaining by guessing, then the person can actually get about 90% of the correct answers. So, to conclude, we take a look at the topics that we have covered in this introductory course. So, we broadly divide the course into the statistics component and the probability component. So, we started with introduction to statistics, what is statistics, types of data, the 4 broad classifications of data, and then we looked at representing categorical variables using pie charts and bar charts, and then representing numerical variables using histograms, stem and leaf and so on. Then we looked at association between categorical variables in the form of chi-square and Cramer's V, and then association between numerical variables in terms of variance, standard deviation and coefficient of variation. Earlier, when we represented numerical variables, we also and categorical variables, we looked at measures of central tendency with mode for the nominal variable, median, the ordinal and interval variables, and arithmetic mean, median and mode for the ratio level variables. Then we went or studied probability, we defined the axioms of probability and the theorems, and we worked out some problems in probability, and then we looked at conditional probability and Bayes theorem. We introduced random variables, their expected value and the variance, and then we looked at association between random variables, trying to find out the correlation coefficient, covariance and so on, and then we studied the binomial and Poisson distributions, discrete distributions, and then we did a little bit of normal distribution in this course. So, with this we formally wind up this course. I hope you have enjoyed looking at these videos and hope that you are able to get introduced to the basics of probability and statistics, which would help you do advanced courses in the future. Thank you.